What if I told you the Earth keeps a diary? Billions of years of history, epic stories of rising seas, shifting continents, and wild climates, all written down. Well, it turns out it's true. And the pages of that diary are the layers of rock right under our feet. Today, we're gonna learn how to read them. Okay, let's get into it.
Just look at this. This isn't some abstract painting. It's a seismic image, basically an X-ray of the Earth's crust. And what it shows is this incredible, complex tapestry of rock layers. But see, it's not just a simple stack of pancakes. These layers curve, they pinch out, they cut right into each other. Every single one of these patterns tells a dynamic story.
So yeah, that's the big question, right? What forces sculpted this amazing architecture? What clues are hiding in all these layers? And, how on earth do geologists figure out this ancient language? That's exactly what we're going to break down. Here's our game plan. First, we'll talk more about this idea of reading the Earth's diary. Then, we'll dive into the main engine behind all this, something we're calling the sea level dance. After that, we'll look for the punctuation marks in the story, the surfaces that act like chapter breaks. Then we get to the chapters themselves, the systems tracks. And finally, we'll see why all this is so important for finding actual buried treasure, like oil and gas. Okay, let's get into the mechanics of this thing. If you really want to understand how these rock layers form, you've got to get a feel for the fundamental rhythm of the Earth's oceans, playing out over millions and millions of years. At its core, it's a really simple, kind of beautiful idea. Just picture a constant tug of war. On one side, you've got the amount of space available for sediment to pile up. Geologists call this accommodation space. And on the other side, you've got the actual supply of sediment, all that sand, silt, and mud that's trying to fill that space. Pretty much everything is dictated by how these two forces play against each other. So what's driving this constant battle? Well, it really boils down to three main controls. First, you've got the eustatic sea level. This is the global rise and fall of the entire ocean, usually driven by huge events like ice ages. Then you've got subsidence. That's the slow sinking of the land itself, which opens up more room. And finally, of course, there's the sediment supply, the sheer amount of stuff being washed down from the mountains. It's the unique mix of these three forces that writes the story in the rocks. So if the rock layers are the pages of our story, we need to find the chapter breaks. In geology, these are called surfaces, and they are absolutely critical for figuring out the plot. And this is really the key idea. These surfaces aren't just random lines. They represent huge events, a massive drop in sea level, a really long period of erosion, a sudden, widespread flood. They separate packages of rock that geologists call genetically unrelated, which is just a fancy way of saying they formed under completely different conditions at totally different times. Now, the most important of all these surfaces, the big one, is the sequence boundary. This is our major chapter break. It's what geologists call an unconformity, which is basically a buried erosion surface. It tells us that sea level fell in a big way, exposing the seafloor and creating a massive gap, a missing chunk of time in our geological diary. And this shows you exactly what we're talking about. This is a real-world sequence boundary. Below that jagged line, you've got deposits from a slow, lazy, meandering river. Then, that surface was exposed and eroded away. When the story picks back up, it's a totally different scene, a high-energy, braided river system. And the line between them? It represents a 7 million year gap in time. A whole chapter is just gone. Of course, not all breaks in the story are created equal. The sequence boundary is like a major chapter break, for sure. But we also have parasequence boundaries. A good way to think about these is as paragraph breaks. They're usually caused by smaller flooding events and don't represent nearly as much missing time. Telling them apart is absolutely key to getting the story right. Okay, so we've found our chapter breaks. Now it's time to actually read the chapters themselves. These are the packages of rock that get deposited between those major surfaces, and geologists call them systems tracts. Here's the most important part. Each systems tract is tied to a specific part of that sea level dance. There's a certain type of rock package that forms when sea level is high, another when it's falling, another when it's at its lowest, and a final one when it's rising again. Remember that term genetically related? This is what it means. All the rocks in one systems tract form during the same continuous phase of that cycle. Understanding these 4 chapters is pretty much the key to unlocking sequence stratigraphy. If you can identify them, you can piece together the entire history of sea level change. So let's follow the cycle step by step.
We'll kick things off here with the high stand systems tract. This is what you get when sea level is at or near its peak. There's a lot of room for sediment, and rivers are dumping tons of it into the basin. The result? The coastline actually builds outwards into the sea. It progrades, creating these really beautiful classic delta shapes you see right here. But then things change. Maybe the climate cools, ice caps grow, and sea level starts to drop. This is the falling stage systems tract, and it's a pretty dramatic phase. As the sea pulls back, rivers start cutting down into that newly exposed land, eroding it and carving out deep valleys. This powerful erosion is what creates that super important sequence boundary we just talked about.
Okay, now we're at the bottom of the cycle, the low stand systems tract. Sea level is at its lowest point. Those rivers that were carving valleys, now they're basically sediment superhighways. They shoot right past the old coastline and dump all their sand and mud way out in the deep ocean, forming what we call basin floor fans. And the valleys themselves, like the channel you see here, are now just pipes for sediment heading offshore.
And finally, the cycle turns around. Ice caps melt, and the sea begins to rise, flooding the land all over again. This creates the transgressive systems tract. As the shoreline moves inland, it lays down this new blanket of sediment that just drapes over the old, eroded landscape. If you look closely at this seismic image, you can see how these newer layers seem to climb up onto the older surface. Geologists call this onlap, and it's a dead giveaway of a rising sea. And with that, the cycle is complete, ready to start all over again.
So why does any of this matter? I mean, it's fascinating geology, no doubt, but it also has huge practical and economic importance. This is how we find some of the planet's most valuable resources.
And here it is, the aha moment. This constant dance of the sea level, it just so happens to be the perfect recipe for creating hydrocarbon traps. The very processes that create these distinct systems tracts are also the perfect conditions for trapping oil and natural gas deep underground.
The recipe is actually pretty simple. You need a rock with lots of holes in it, like sandstone, to act as a reservoir to hold the oil. And then you need a rock that's not porous at all, like a mudstone, to sit on top and act as a seal to trap it. Sequence stratigraphy is the treasure map because it predicts exactly where you'll find these perfect layers of sand and mud stacked on top of each other.
Let's go back to our low stand systems tract for a sec. Remember that big valley the river carved out? Well, it often fills up with really nice, porous sand. And then when the sea rises during the transgression, it covers that whole area with tight, impermeable mud. And just like that, voila, you've got a perfect reservoir rock, the sandy channel, totally sealed up by mudstone. That's a prime target for exploration. And you know what's really amazing about all this? It's not just ancient history. When geologists say the present is the key to the past, they mean it. To understand an ancient high stand delta buried miles underground, they go study the modern Mississippi River Delta. To figure out how a transgressive coastline deposits rock layers, they look at places like the barrier islands on the US East Coast. The world today is a living laboratory for understanding the past. Which brings us to one last big question. Right now, we are in a period of rising sea levels. We are living through the formation of a transgressive systems tract. So what story will our time leave behind in the rock record for future geologists to read millions of years from now? What is our chapter in the Earth's diary going to say?